Right. So the last talk is going to be an online talk. It's going to be very much in the same line of things that Julia was talking about at the end of her talk, I think. So we have Hlér Kristjánsson, who's going to I guess tell us about implementations of the switch and whether they're the status of whether they're realizations or simulations. I can't remember his title, but I believe that's the subject. There you go. On the practical realizability of indefinite causal order and its applications. So we're listening. I think everything is set up so we can see you here.
Hi, hi everyone. Can you hear me?
We can.
Great. Yeah, let me know if I need to speak louder or quieter.
That's fine.
Okay, so thank you very much for introduction, Alistair, and thank you to Vilasini for inviting me here to talk about this topic. Quite a difficult and complicated topic to talk about. Yeah, I'm very sorry I can't be with you here in person. I just moved to Tokyo, as you can see here behind me, and it would be a bit far to come back just a few weeks later back to Europe. So apologies for that, but I hope we can have a fruitful discussion in this talk and questions, and also in the panel session afterwards. So first of all, thanks to Julia for explaining half of the introduction to my talk already. So a really nice talk, really nicely presented about all the experiments and what the quantum switch is. So in this talk, I'm going to talk, as Alistair said, about the practical realizability of indefinite causal order and its applications. So some sense related to Julia's talk. Now, this talk is not going to be based on any particular paper or set of papers, but rather it's going to be a kind of overview of the literature. So I thought, this is the last talk of the conference, and a very heated debate has gone on. So I think maybe the best idea was to really try and give an overview, and then maybe try and find some sort of resolution by putting all of those arguments into some sort of unified framework. So I'm going to start by giving a review of what the quantum switch is, applications, experiments. Then I'm going to discuss the debate, which Julia already mentioned. First, I'll sort of distinguish between 2 points of view: a spatiotemporal view on the experiment and a sort of dynamical or information-theoretic view. I'll discuss kind of the arguments for and against each one and try and reach some conclusion. And then finally, at the end, I'm going to say a few things about some computational advantages of the photonic quantum switch and what the implications are of this theoretical debate on whether or not these advantages can be realized in practice or to what extent. And as I said, this talk's going to be based on some of my own works, works of some other people on both sides of the debate, as I've written down here, and discussions with various people. So let's start with the quantum switch supermap. So, well, we already know what it is from the last talk and the last week. So just a few quick clarifications. So in this talk, I'm going to write the supermap as this kind of blue object. And the supermap is just a map that takes quantum channels as inputs and spits out another quantum channel in a well-defined way. And in particular, the quantum switch is a supermap that when it takes 2 unitaries U and V out, it returns a quantum superposition of the 2 circuits implementing UV or VU, conditional on some control qubit. Now, 2 points of clarification. So when I say supermap, this is equivalent to process matrices. It's just a choice of process matrices. And secondly, you may have heard of this scenarios of computation. So in computation, you have kind of a big experimenter who kind of just sticks slots into his or her blue quantum computer that implements a quantum switch. And the alternative view is that sort of there are some agents, one performing U, typically called Alice, and the Bob performing V. And it turns out that those 2 notions are also equivalent notions. So in both cases, you have sort of some certain well-defined freedom to apply each of the 2 operations, and the supermap or the process matrix connects them in some particular way. So as we already heard earlier, quantum switch cannot be written as a quantum circuit or any probabilistic mixture of quantum circuits with a single slot of each of the 2 unitaries U and V. So that's in some sense what defines the indefinite causal order of the quantum switch. Now, the quantum switch has been shown to have a whole host of information-theoretic and information processing advantages. So we know that there was a paper showing that if you have access to the quantum switch, it can perform discrimination of some unitaries, whether they commute or anti-commute. Then we have this communication complexity result. We also have channel capacity activation results, where if you combine two noisy channels inside the quantum switch, the noise can be reduced. And even quantum metrology and thermodynamics have been areas where the quantum switch has been shown to have some sort of advantage compared to causally ordered processes. But now we might ask, okay, let's just be clear. What's the purpose of studying these advantages? And there are two very well-defined different purposes. The first purpose that one might have is to better understand quantum theory by comparing it with suitable alternatives. So maybe like GPTs, PI boxes, same sort of study. You're trying to study quantum theory by comparing with all possibilities that may not be quantum theory, may not be the standard quantum theory we have. And the second motivation is really related to how to implement these advantages in practice. So you can ask, like, I've got all these theoretical results, but can I actually use them in practice? And maybe I can build, a quantum switch startup where I start selling quantum switches to JP Morgan to earn more money in the stock market. So I want to know, can I do that? And that's a fundamental question. Now, that's a very different question to the first one, because here we're really interested in the real world, whereas in the first motivation, we're interested in some theoretical things. But as we know, if we want to make our quantum switch startup to sell quantum switches to earn money on the stock market, we need to be able to build the quantum switch. So if we want to build the quantum switching experiment, we need to know that we can actually implement it in indefinite causal order in the lab in our world, which is Minkowski spacetime. So in terms of experimental proposals, first of all, there are experimental proposals involving exotic gravitational effects, like Lucy and Hardy's initial proposal, and two papers I cite here in the notes. But these are just science fiction as far as practical implementation are concerned. They're very, very important proposals for understanding theoretically what's going on. But if we want to actually implement or gain some advantages, then we need to implement them in Minkowski spacetime. And typically that's done using single photons. And I won't mention the details of those experiments anymore, because we had a really great talk about that earlier. So if you just remember the previous talk and all the references therein, then that's basically the experiments I'm going to talk about. Now, they have been performed, and as Julia mentioned, there has been a debate to what extent these advantages, or rather the experiments themselves, implement indefinite causal order, really indefinite causal order, or maybe indefinite causal order in some sort of weak sense, or maybe not at all. So in this talk, I'm going to try to unpick the fundamental premises of the different arguments for this sort of whole spectrum of viewpoints on this. So let's start with the causal relata. So what are they? Well, that's the cause of the disagreement, as far as I would say. And that sort of, this point of view came from Nick Ormrod's and Augustin van Uytterweld's paper just a few months ago. Nick was the person who just asked the question earlier. And I think that this is quite a nice characterization of the disagreement. So the causal relata are things that bear causal relations to one another. So before we can even start talking about indefinite causal order, we need to know what is the indefinite causal order of what. So that, I think, is the fundamental question. Well, wait a minute. Is that really the fundamental question? So what if we want to make our quantum startup to sell quantum switches? Then who really cares the indefinite causal order is implemented or not? We just want to know, does this photonic quantum switch subroutine have some computational advantage? So that's a kind of different point of view, which I'll try and discuss later. But I would argue that from understanding the theoretical point of view, we should be able to answer this more practical question as well. So, maybe at this point, are there any questions about what I said so far?
I don't think there are any questions from the room.
Okay, if not, then I'll continue with the first viewpoint. So the first viewpoint I want to discuss is the spatiotemporal view. So this view basically says causal relata are space-time events, and that's the end of the story. And second premise is that causal order in an experiment is defined by the relativistic light construction of the experiment. Okay, so these are sort of just definitions, if you like. And the third premise is that in the photonic experiments, there are 4 space-time events with a well-defined light construction. And then the fourth, the conclusion follows directly from those 3 premises, namely that the causal relata in the photonic experiments are actually in a definite order. So if you believe the first 3, then the last must follow. And so let's try and unpick those things. So 1 and 2 are just definitions. So 3 is a contentious point. So in the photonic experiments, this view says there are 4 space-time events with a well-defined light structure. So if I imagine I have Julia's experiment, and there is the unitary U on one side and V on the other side, then my photon goes to U and then to V. In one arm of the superposition of V to U, the other one. So note that it's a space-time diagram. So when I draw 2 U's, it's actually the same physical device implementing it. It's just the up axis is just time. But the point is that since I'm just drawing space and time, there are actually 4 space-time events, because space-time events are defined as points in the space-time diagram. So there are 4 events, even though there are 2 devices. And so by this view, that kind of says no indefinite causal order. But already in one of the earliest experimental papers, there was an objection to this view, in fact, a very strong objection, saying that, in fact, the space-time view not only doesn't tell the full story, but is actually completely inconsistent. And they argue that we need to reject premise 1, or what I call S1, a spatiotemporal view, because individual space-time points have no operational meaning in the experiment. Right? They say any attempt to physically distinguish the 2 times at which a photon can pass through the gate would reveal a which-way information and thus destroy the interference. And so, subsequently, another paper by Pankovic and Vojinovic indeed did propose a protocol which, in principle, could distinguish the individual space-time points. And so we recover the fact that, okay, maybe it is consistent to believe premise S1, and therefore the space-time spatiotemporal view is consistent. And if we believe it, then there is no indefinite causal order. But even if we believe the spatiotemporal view as being valid, we could just as well have another view, a dynamical view, which could be equally valid. So we can just as well, we better examine that view as well. So what I would explain now as a dynamical view is the kind of simple example of a kind of typical statement of this view. And later, after some objections, I'll refine it to Ognian Oreshkov's sophisticated view, which is a bit more complicated. But the simple version is basically that the causal relata, remember, are no longer space-time points, but operations performed by agents. So there's some quantum channels, i.e. dynamical objects. And so we call this a dynamical view. And again, this terminology is due to the recent paper by Nick and Augustin. So second premise is that causal order in an experiment is defined by the causal structure of a supermap that describes the experiment. So in this case, we would say the supermap is the quantum switch, for example. Third premise is a experimentally verifiable fact, namely that the photonic experiments are described by some supermap acting on the channels that are performed, and the output of the whole experiment is the quantum switch. Now, this is a kind of uncontentious claim. Everybody agrees that the experiments output the quantum switch. The question is whether it's, the kind of debate is whether it's actually the real quantum switch acting on 2 channels or some other supermap that takes more than 2 channels as input. And so premise 4 is precisely saying that it is a kind of contentious premise, which is saying that in the photonic experiments, only 2 operations are performed, one per channel. And then the conclusion basically follows that in 5, that since the quantum switch cannot be realized as a circuit with definite causal order without at least 2 uses of at least one of the channels, then it follows that the experiments realize an indefinite causal order of the causal relata. Okay, so let's investigate the contentious claim in a bit more detail. So this claim is that in the photonic experiments, only 2 operations are performed. Now, the argument, or the sort of simplest argument for this goes in the following. The photon only interacts once with each optical device. Now, let's go back to the spacetime diagram. So if we look at the green path, so then we have first going through V and then through U. And so at time t2, it interacts with U. But in that branch of the superposition, the photon is not going through U at time t1, but it's just a vacuum going through the U at time t1. But the vacuum is not doing anything. This optical device doesn't change the vacuum. And so it's a trivial interaction, so it doesn't count. And the actual operation that we care about is only performed once. So that's sort of the core of this, at least the sort of most basic argument for the dynamical view of causal relata. But I will now object, and I will say, wait a minute, it's not correct the vacuum interaction is non-trivial. The vacuum interaction is only non-trivial when nothing else is going on. But as soon as you have a superposition of the particle and the vacuum, which you have in these experiments, and the vacuum interaction is non-trivial. So to understand this, let's take a little detour away from indefinite causal order. So forget indefinite causal order for like 2 minutes, and we're going to talk about something completely different, so, namely the coherent control of quantum channels. So this is like some quantum information protocol. So the question is like, let's say I have some unitary U that's given as a black box. Can I construct the controlled version, the control U? Well, as Akihito Soeda showed in 2013 and several subsequent papers discussed, this is impossible because a unitary U is only defined up to a global phase, but in a controlled unitary, there's a non-trivial phase between the vacuum and the particle, as you can see in this equation over here. So it's not possible, given a unitary, to construct its controlled version because this phase is not well defined unless you actually define it. So in one of my first papers with Giulio Chiripella, we showed that there's a natural way to kind of circumvent this this problem, which is that maybe instead of starting with a black box unitary U, we can start with sort of I don't know, something we can call like, let's say, a gray box. So this is sort of a unitary that's block diagonal, and in one block we have the original U, and in the other block we have just some other unitary. And if it's one-dimensional, then the unitary is just a complex phase. And then we can make use of this, the fact that we have this complex phase already inbuilt inside the matrix with the actual degree of freedom that we have introduced. It's already inbuilt with respect to U, and this would allow us to create a controlled unitary because the phase is already defined. And interestingly, this sort of scenario appears naturally in quantum optics because if U is some unitary on the polarization of a single photon or any internal degree of freedom, then the e to the I theta part of the unitary, this bottom right corner, would just be the vacuum. So we see now that any unitary U on the one particle sector is in principle implemented by some larger unitary that also includes an action on the vacuum state. And this action would be trivial if you didn't care about the vacuum, but if you are doing superpositions of vacuum and particle, then there is this non-trivial phase which needs to be taken into account. And this can be implemented in a bit of a complicated, well, not so complicated, but mathematically involved way, which I don't have time to explain now. But the main point is that the mathematics is just translating a control and target system into an interferometric setup. So basically you say the control is in 0, my particle goes to the left arm of the interferometer. If it's in 1, particle goes in the right arm, and then I just stick my U tilde, then it's a new big unitary on the right arm, and then I get the control unitary with some well-defined phase. Now, in our works, we showed that this coherent control of 2 channels has many advantages in quantum communication, and in general, it's sort of a fundamental building block in if you want to build a quantum functional programming language, which is something that I'm interested in working on at the moment. But the more crucial thing for our purposes here is that this framework can actually simulate the quantum switch. So if I just put 4 of those vacuum extended unitaries, 2 U tildes and 2 V tildes, onto the interferometer, as I've shown here, then we simulate basically the quantum switch. Now, the physical operations that are applied here are the vacuum extended unitaries. And each one is applied twice. Now, crucially, this physical scenario that I've described, this model can very well model also the experiments, the quantum switch, even where the devices are in the same place. So even if there's only one physical box U and one physical box V with a loop, because the circuit here is just telling you, is again sort of structured like a space-time diagram. So the 2 uses of U are just uses of the device U at 2 points in time. And so this circuit can naturally model the photonic experiments. And therefore the question arises, okay, if I have this model of photonic experiments, and I see that there's a non-trivial interaction at each unitary with the vacuum, then really there should be 4 operations being applied in here. Even if I forget about the fact that it's a space-time diagram, I don't care about space-time. I'm just saying I now just think that these are operations, and then I see that there are actually 4 non-trivial operations going on. And so this argument would be an argument against premise number 4 in the dynamical view. And so this argument would go on to then reject the claim that indefinite causal order has been implemented. Now, however, do note that since on both arms of the interferometer there's both a U and a V, the overall relative phase of each of those unitaries actually cancels out. And so that's why it can be equal to the quantum switch. The overall thing doesn't depend on any of those phases that I just mentioned. And this leads us to the next kind of counter argument, which is basically the kind of argument by Ognian, who I think is here. And so I will now sort of rephrase Ognian's argument into the framework that I just sort of wrote up. So apologies if it's not perfectly precise, but yeah, I wouldn't have time to describe the entire argument. But the main point I would argue is the following, that, okay, let's now say that the causal relata are actually possibly time-delocalized operations performed by agents. So what are these time-delocalized operations? So if I imagine some sort of concatenation of controlled unitaries, so controlled unitary on the 0 state and then on the 1 state, I get some sort of a quantum comb, if you like, which I've drawn on the left, so the red thing on the left. Now, Ognian argues that this is in fact, that should be considered as one operation. And in the experiment, there are just 2 of those time-delocalized channels, or in fact, you can do the experiments with only 1 of them and 1 ordinary channel. And the crucial point is that each of those channels can, in some sense, be seen as isomorphic to an ordinary unitary U. So I've shown that isomorphism here in the simplest way. You just stick a wire between inside the slot, and then you get back to the ordinary unitary. But in the quantum switch, it's a bit more complicated. Now, basically, you now sort of modify also a 4th premise. So remember, the 4th premise was that there are 2 operations per channel. Now we say there are 2 time-delocalized operations per channel. And the argument is something like this. So now if I just draw my experiment using these sort of time-delocalized channels, well, I can actually, simplest version would involve just one time-delocalized channel that is sort of, and Bob is sort of sandwiched in the middle between them. But then I can sort of write down all the system labels of the control, target, input, output, Bob's, input, output, etc. Compared with the supermap that is equivalent to it, acting on the ordinary unitaries. And I can identify, there's the control here, and there's the control there, and the target there, and the input and output, Bob's output, Bob's input. But where's Alice? Alice looks like she's disappeared. So poor Alice has gone from the picture. But Ogden makes the nice point that you can do some little mathematical gymnastics, and you find that the algebra of operators on Alice's input is precisely equivalent to some very non-trivial combination of control and target inputs and the output of Bob, and similarly for Alice's output. And so since we can identify Alice's input and output operations as sort of delocalized operations around Bob before and after him, then the argument it goes that this time delocalized operation really should be considered as one operation and equivalent to an ordinary one operation by one of the agents. So now this seems like a very strong, and I would argue this is the most sophisticated argument for the implementations of the quantum switch, being genuine implementations. But of course, there has to be some more argument. So recently we had this paper by Nick Ormwood and Augustin van Rietveld, and they basically argue the following. So they object now not to D1 or D2, i.e. dynamical premise 1 or 2, but dynamical premise, 1 or 4, but actually to 2. Now, what is 2? 2 was the fact that causal order in an experiment is defined by the causal structure of a supermap. That describes the experiment. And I think actually Nick basically already said this in his comment earlier. But the point is that they argue causal order in an experiment is defined by a supermap that not only models a particular fine-tuned run of the experiment, but models an appropriately broad range of physically possible transformations in the experiment. So they argue that if we are considering time delocalized channels, we should in principle also consider the possibility of more general time correlated channels where Alice can apply a U1 at the first time step and then U2 at the second time step. And they argue this really, if you like, because the point is that possibility of performing operations is essential for causality. So the point is that you cannot talk about something influencing another thing unless you consider all the possible things that could physically happen or are allowed to happen in the two instances. And this leads to quite another sophisticated argument that I unfortunately don't have time to go into all detail of about fine-grained versus coarse-grained causal structures. But if you read the very long paper, you'll find that there is this formalism presented called the rooted quantum circuits, which we worked on together some time ago, and then they extended basically the framework of quantum causal structures using rooted quantum circuits to the case where we have sectorial constraints, so systems similar to the quantum switch. And the conclusion is basically the following, that the physically fundamental fine-grained causal structure of the experiments is definite by the previous argument of rejecting premise D2, but they find that and define a well-defined sort of coarse-grained concept of a coarse-grained causal structure where the sectorial constraints are ignored, which essentially corresponds to Alice's two possibly different channels treated as the same. And they show that this coarse-grained causal structure is in fact indefinite. So there is a sense in which the experiments are both realize indefinite causal order in a coarse-grained sense, but are when you look really closely, they are finite. It's definite. The causal structure is definite. Now, interestingly, a separate paper that appeared just a couple of weeks earlier by Vilasini and Renner argues for basically the same distinction and the same conclusion with the fine-grained versus the coarse-grained causal structure. And they use a completely different framework, namely causal boxes and some other techniques, but and the argument is slightly different, but very interestingly, the conclusion is essentially the same. So now, where does this leave us? So the question is still, to what extent is indefinite causal order implemented in the photonic experiments? Well, I will argue now that this depends on the context of application. So if we are considering fundamental physics, then I argue that the spatiotemporal view, this is a valid description. We have rebuked the argument against it that it's invalid, but I think it's one possible valid description. And I would argue that this is the description that is most consistent with usual fundamental physics. In fundamental physics, we don't treat one particle or vacuum differently. They should all be treated on an equal footing. So this is sort of the most natural way, I would say, to describe the experiments in the context of fundamental physics. And in that case, indefinite causal order is not implemented in the photonic experiments. And if you follow the arguments and accept the arguments by Vilas and Aranda, then it also follows that they cannot possibly be implemented in any experiment in Minkowski spacetime. However, if we are thinking about information-theoretic settings, and maybe at the end of the day, information theory is more fundamental than fundamental physics. I mean, that's an open question. But for now, let's just think that we have information theory settings. Then I think the dynamical view will be the most appropriate, and it's consistent with an account of agents making interventions. Now, if we're interested in all possible interventions, not just the ones that you can implement in a particular experiment, but really all physically possible interventions that do not violate the laws of physics, if you like, or at least within the scope of the experiment, then we would argue that indefinite causal order is not implemented in the photonic experiments. However, if we are interested in a particular restriction of the experiments, where we think of each agent having access to just some fixed time delocalized channels, then this coarse-grained dynamical picture may be appropriate. And then we can argue that indefinite causal order has been implemented in the experiments, just like in the experiment that Julia presented earlier. So this is my take on the conclusion, and which is sort of trying to kind of resolve this conflict. But if you remember, we had the quantum computing company asking us, what about the advantages? And so I think I have a few more minutes. So I'm just going to spend a couple of minutes describing the point of view of information processing advantages. So similarly to the conclusion I just made about whether or not indefinite causal order is implemented in the experiment, I'm going to argue that whether indefinite causal order is useful also depends on the task and the available resources. So first of all, as we already heard, I think many times this week, it's well known that the quantum switch of two unitaries, U and V, can be simulated in an ordinary quantum circuit with definite order if at least one of the two unitaries is used twice. Now, what if instead we have some time delocalized channels? So if we start with the time delocalized channel, then the question is, what is the computational power of this thing? So what can we do with the time delocalized channel? Well, an important observation, which Ognian also made in his paper, is that the time delocalized unitary can be simulated using two copies of the unitary U. So if I have a unitary U and I wanted to remember in the original quantum switch, I only wanted to use it once. In the simulation, I use it twice. Now, if I have a simulation, I can simulate also the time delocalized channel. But crucially, if I only have access to a time delocalized channel, I cannot generate from one time delocalized channels two independent copies of the original channel. So if I have a time-delocalized U, I cannot generate two copies of U independently. Well, this gives us a sort of hierarchy of computational resources. So we see that the time-delocalized channel requires less resources than two copies, but more resources than a single copy. So any photonic subroutine that implements the quantum switch that's given access to time-delocalized unitaries, in principle, has advantage over a subroutine that requires two copies of the unitaries. And similarly, access to time-delocalized channels in a photonic setup can reproduce the capacity advantages in communication, the quantum switch. Now, this will be useful if time-delocalized channels are a genuinely naturally available resource. And from the previous talk, I believe that it may indeed be so, because as we saw in the photonic setups, it is not really natural to have, you have those unitaries implemented by some optical elements, and it's not natural to change them all the time. The time scale at which even error would occur can be much bigger than the time scale over which you send the photons through. And so it seems like maybe time-delocalized channels really are a natural resource in computation. And then in that case, we can say that the advantages of indefinite causal order may be implementable in practice, at least to some extent. But if we know about time-delocalized channels and we can do them, well, we could even ask, since if I have a photonic setup that can implement the quantum switch, then why not also do something more? Like maybe I can implement quantum advantages of the quantum switch, but I can also implement other advantages, which Julia also mentioned earlier, from just a more general coherent control of quantum channels. So, for example, if I have just take a time-delocalized channel, which was a U and the U, and now instead I have instead of the U and same U and the U, I have some dephasing channel, which is either I or Z on the one particle sector and with some non-trivial phase in the vacuum. And now I say that it's used at two time steps, and it's anti-correlated. So every time I have I first, I have Z later, etc. Well, then we proved we will prove in an upcoming paper that in fact you can get perfect quantum communication through this dephasing channel, even though when you use it only once, one time step, the noise is completely dephasing. So it's kind of a perfect activation. And so this is possible just with one time correlated channel where you allow the changes to happen in the process of the two time steps. And crucially, this is impossible using setups like the quantum switch, where the noise is directly correlated. So maybe this suggests that maybe one of the biggest highlights from the study of quantums in the quantum switch and indefinite causal order in the causality community may, for applications, actually be not only practical applications of the quantum switch, but also, or at least, practical applications of related schemes that were proposed by Alistair, in fact, and co-workers and many people afterwards for capacity activations, or even related schemes for quantum computation that maybe have been inspired by the quantum switch. So, to summarize, there are two views to view the indefinite causal order experiments: the spatiotemporal view and the dynamical view. And they are both valid views, as we have seen. But under scrutiny, it appears that the fundamental assumptions of both views lead to the conclusion that indefinite causal order is not implemented in experiments in a sort of fundamental sense. But there is a coarse-grained notion of indefinite causal order that's been developed just in the last few months, which can be said to really be implemented in a genuine sense in the photonic experiments, and which may indeed also be appropriate in information-theoretic settings. Now, time-delocalized channels are more generally vacuum-extended time-correlated channels, which are available in the photonic experiments, can provide a powerful resource in information processing tasks in the real world. So maybe we will see eventually a quantum switch startup coming about in the next few years. And so I will end with an outlook. So I think from what we've seen about the debate, I think a few things to look at would be trying to understand what indefinite causal order means in exotic physics implementations. And also maybe trying to apply the above analysis to quantum switch implementations in the gravitational field of the Earth, just a recent proposal. And finally, something that would be very interesting to continue working on is further theoretical and experimental work in understanding the computational power of time-delocalized channels, or even more generally vacuum-extended channels. But in particular, for the quantum switch implementations, time-delocalized channels and their computational power would be a very interesting thing, I think, to study, to really understand the ultimate limits of what we can achieve using the photonic indefinite causal order. So with that, I would like to thank you for your attention.
Thanks a lot, Hlér. I saw that Ognan had a question in the chat, but maybe I'll take a question from the room first before we give the microphone to Ognan virtually.
Hi, Hlér. Charles speaking. Thanks for a clear presentation of various arguments, let's say critical arguments about implementation of the switch. Now, I think we all agree that what have been implemented so far is not the mathematical switch, let's call it, as it was in the original paper. And in fact, I would be interested to hear at least once what would be an implementation with no borders of gravity or whatsoever. I know about the time like curves, but I guess we could do also more interesting things if we had access to that. But in the meantime, we have some implementations that we might call it differently, but nevertheless interesting. Now, first I need to a little bit deconstruct this space-time argument. And all confusions come from not distinguishing between the notion of events and the location of events. And we can still think about two events in the sense of the physical operation of happening or CP map that happen in four space-time space-time points, sorry. And this is the proof of Voinovich and Ponkovic that they require four space-time points. There is no doubt about that. The only doubt is there are two operations or four operations. And if you know from in a GR, the event is defined, the point in a manifold doesn't have any meaning. It is always physically represented by coincidences, for example, of the fields. And these fields are usually then classical. That's why it very often boils down to just a point. But the field in a quantum switch is not a classical. These four lines, one blue and one red, these were not two fields. That was a single photon in a superposition. And it was delocalized. And that's the reason you, at the end, although you have 4 points, they are just two operations. Now you have another argument about extended unitaries, which I think you answered in a sense that Ognjan's paper treated correctly as two extended unitaries and not four of them, and I don't want to comment on that. And I find I'm coming now to the last point, and the last point is most interesting to me, and I think Julia addressed in a certain sense. So there is this setup that if you have if you can change your local operations sufficiently fast, then you can turn into something which doesn't look like a switch, and it's causal. And here I think it's a very interesting point, and I would like to understand it better in terms of the identification of an agent or identification of the same operation. And I would say by definition, if you allow to do that, and you have short operations that you distinguish these two moments of action, this will be, by definition, be a four-party process, a very interesting one, but not two. By the mere definition of the same operation, extending of them, you talk about two agents. So I would see these implementations as something which is providing a larger set of possibilities. Being a genuine switch in the optical sense, and yet being also rich for something else. And my last comment is that I think there is this kind of idea that gravitational switch is very different, or this exotic spacetime that we considered so far. And I have to disappoint people. There is some difference that was not mentioned here about the difference in proper time and coordinate time. But nevertheless, the picture from somebody from far away is exactly as the one you have next to you. All your comments can be applied also for the gravitational switch.
I think now we can take a question online. Ognan wanted to have a question comment.
Maybe I'll just reply to
if you want to make a comment.
Thanks, Chancellor, for the really nice summary of the talk and sort of your thoughts. So I think I basically agree with most of what you said. But I would say I don't know what a real quantum switch implementation is, and I'm not an expert on quantum gravity, so I wouldn't be able to comment on that front. And I think, so yeah, I mean, my analysis, as far as I was saying, it applies to the optical sense, and I have indeed heard previously from other people as well that the same arguments can be applied against the gravitational implementations. But I would say that the optical implementations and the quantum switch have been around for quite a long time, and maybe I'm sure there is more work to be done to really understand whether some sort of gravitational implementation that approaches the kind of really gold standard implementation of closed time-like curves would be possible. And maybe it's not possible. Maybe it's just absolutely impossible. But I would say that maybe it would be interesting to see to continue to see if that could be done.
Okay. If Ognan, I don't know if he wanted to ask a brief question, because there are also a couple of questions from the room and also other questions online, and we're at the end of the time. But seeing as Ognan was very quick getting in.
Me because I'm in the train and the connection.
Yeah.
Hi, Ognan. Thank you very much. Thank you very much for coming to my talk, even though you're on the train. I really appreciate it.
I found it very interesting, actually. Thank you. And I want to make a comment, actually, about this idea about the fundamental. Mm-hmm. It's not realization, or it's a kind of weak realization, even if we accept the time-delocalized system picture. Mm-hmm. Yesterday, I spoke length about this, and what I understood is that basically, when one speaks about this coarse-graining, what one is referring to is really two different descriptions of the same more general process, which by definition is defined on these super selected nodes. And I think it's important to emphasize that these are not the same nodes as the time-delocalized nodes that which I claim that actual switch is happening.
Sure. Mm-hmm.
Yes. However, there was this idea about the fact that one description is more informative than another. And in that sense, might say, okay, I have a better, more informative description, although that's not necessarily related to that. We can observe that indeed there is this embedding in a causal circuit, which in some sense needs a totally causal description and is more informative because I can understand the switch inside. And one thing I wanted to emphasize is that the question about causal non-separability has always been about whether a certain type of embedding is possible. Because when we define what is a causal process, causally separable process, it's about the fact whether it is compatible with a certain type of embedding. Again, something that could be described by a circuit where you have a classical bit or classical variable that determines essentially the time at which certain operation happens. Does the process admit this type of embedding? And in that sense, I would say that these experiments are completely compatible with the claim that this is a causally non-separable process. But now I understand that the idea behind all of this business with the fundamental realization is this idea that maybe you could have a realization of the switch where it actually does not exist a kind of a causal explanation. There is no embedding in anything that we can find. So my question is, how can one define that? Because in an operationally meaningful way, because how can you ever be certain when you do this experiment that there does not exist a physical process around that would actually admit this type of causal explanation, just like the more informative process that we have about the experiments.
Yeah, thank you very much for the comment. The question, I don't know. That's a very difficult question to answer. I mean, I suppose in the experiments that have been done so far, we have a kind of well-defined theory of quantum field theory on Minkowski spacetime that can explain everything that we've seen before, and so we can argue that from this perspective that has been argued recently, we're talking about fundamentals, and that Minkowski spacetime we know can embed the experiments that we described, but perhaps if we had access, let's say if we had access, okay, we don't, but if we did have access to some complicated structures with black holes creating closed time-like curves. Now, obviously we don't, but just saying in principle, if we did, then perhaps we would not have any theory at the time. There would be no theoretical way of explaining how the experiment comes about in any causally ordered physics, because we don't have such a theory at the time. So maybe in the end it's a question of best description of the physics given our current knowledge.
Okay.
In relation to that, there's also.
Ognan, may I interject? Sorry, so we're already relatively over time, and Hlér is going to be in the panel as well this afternoon. So I think there's a lot of interest in this discussion, but I don't think we're going to stay another 20 minutes, and I think there are several other questions. So what I propose is, if people have any longer comment questions, that they save them for the panel later today. And if there's, I could take one, if someone has a short, precise question, I can ask it now. Otherwise, I propose we save it for the panel, or people can stay and chat if they wish with Hlér. So are there any quick questions or? No. So otherwise, I propose that we thank Hlér and all the speakers of this session.
Thank you.